Hello, everybody. Mr. Danahauer here, coming to talk today about atomic structure. So we're going to learn quite a few different things. There's going to be a lot of vocabulary today, a lot of terms, and some processes even. So you're going to need a few resources to get us going. The first thing you're going to need, as I'm showing you, is a periodic table. The second thing that you'll need is the note guide that you should have been given, or a piece of paper if you're just taking some notes on this stuff. So we're going to go through, we're going to talk about a few different, a little bit of information about the different subatomic particles that make up atoms, how we discovered the structure of the atom a little bit, and then we'll take some time to talk about some different terms like ion and isotope and what does it mean if an atom has a certain number of protons or neutrons or electrons. So let's go ahead and get started. The first thing that I want to do is make sure we have defined what an atom is. And so an atom is really the smallest unit of matter that retains its physical and chemical properties. And what I mean by that is if I have an atom of, let's say, carbon, and it has certain chemical and physical properties about it, if I start to pull that carbon atom apart, it's no longer going to retain its same properties. And so let's go ahead and jot that down first. What is the definition of an atom? And that is the smallest unit of matter that retains its physical and chemical properties. And I have that written down for you. Let me get my slideshow up here. So here we go. All right, so we'll skip this part. I'll come back to that in a second as we get this written down. Okay, pause for a second and we'll get that down. Let me go back to the previous slide real quick. We've talked a little bit about some of these ideas already in previous lessons, but if we say all matter is made up of atoms, that's the smallest unit of matter that retains its shape, or that retains its physical and chemical properties, what is that? How would we classify that statement? And remember that that is a theory. It's a theory because we cannot directly observe atoms or molecules. They're just too small. Even with our strongest microscopes, electron microscopes, we really can't look and see the pieces that make up atoms, and we can't see what happens if we change them. We have to test things indirectly. So here's the thing, though. A lot of people will tell you that this is a fact, right? All matter is made up of atoms is a fact because it's so well stated and studied and holds up over the course of time, that it truly is a theory based on our scientific definitions, but we could almost consider it factual because there's so much information that supports it. So now that we have our definition of an atom down, let's go ahead and talk about the three subatomic particles and where we find those in an atom. Obviously, atoms are very, very, very small. And in fact, they're so small, like you and I can't even really understand how small they are. And so if I was going to draw a picture of an atom, it might look something like the slide I'm showing you. And let me just give you another example of how I might draw that. All atoms, here's our periodic table here, all atoms are made up of three subatomic particles. And so I'm going to label those protons, neutrons, and electrons. Okay. Protons, so if I was going to draw a picture of an atom, the protons and the neutrons, these two guys, are found in the nucleus. So let's draw that really quick. You've got a spot on your notes to do that. I'm going to draw an atom that has two protons. And I'm drawing those in the nucleus right now. You'll be able to tell in just a second. And then I'll also add a couple of neutrons to that. And I'm going to make those orange here. All right, those are also in the nucleus. And then the other subatomic particle we have are called electrons. And those are going to be out here. Oftentimes you'll see them drawn in a circle or a spherical shape. Sorry about the drawings here. I'm drawing on an upright screen. And we'll see those electrons in here. So this is our basic structure of an atom. These are our electrons right here. Okay. And then our protons and neutrons, protons being the pink ones and neutrons being the orange ones here. And those are what we call the nucleus of the atom. And so, as we're kind of going through these structured questions I have for you, the subatomic particles, protons and neutrons and electrons, are subatomic because they're like below the size of an atom or below what makes up an atom. So we call them subatomic. And so, protons and neutrons are the two subatomic particles that are found in the nucleus. Electrons are actually found what we call orbiting the nucleus. So if you want to picture it sort of like the planets that are orbiting the sun, right, or the moon that's orbiting the Earth, that's one way to think about where electrons are. But they're actually the specific location that we give to electrons is called energy levels. And so we find electrons in their energy levels. Okay. Now, if you take chemistry, you're going to learn a lot more about energy levels. But one thing I'll tell you right now is that every atom has multiple energy levels, and they are sort of like rungs of a ladder. They're farther and farther away from the nucleus. Or if you want to think about a racetrack, it's like a lot of racetracks. One inside of the next, and so forth. And so these electrons are moving very fast in these energy levels. And as you get into higher level classes, you'll hear people talk about orbitals, and there are orbitals within each energy level, and it gets a little complex with electron configurations and whatnot. And so we won't get into that in this lesson. So that's our basic structure of the atom. If you want to pause for a second, draw that, and then answer those couple of questions about where we find those, take a second to do that. Okay, the next thing is, what are some things we know about protons, neutrons, and electrons? And the first thing we'll talk about is charge. So protons start with a P, and so we can remember that protons have a positive charge. So I'm going to put that in parentheses next to protons. Protons always have a positive charge. Electrons are sort of opposite in charge of protons. So electrons have a negative charge. We'll write that off to the side here. Okay, electrons are negatively charged. And then neutrons are named sort of after their charge. What does neutron stand for? It's like neutral particle or small particle that's neutral. And so I'm going to put no charge for neutrons because they don't have a charge. Now, this is really important in terms of the structure of the atom and how it stays together. And when we look at bonding, there's so many different things that rely on the charges of the protons and the electrons. We'll see that as we get farther into it. But I do want to mention one thing that's really critical for like lots of science concepts, and that has to do with charges. Remember that if I have a positive and a negative charge, uh, opposite charges attract each other. Remember that term, like opposites attract. So you can remember if I ever have a negative charge and a positive charge close to each other, close enough, they're going to want to go towards each other. There's an attraction together. So I'll draw some arrows coming together. But if I have two like charges, they're going to want to repel each other. And so if I have two positive charges or I have two negative charges, they're going to want to move away from each other. This, guys, is like a critical concept in so many different science topics. That I mean, we'll talk about that a lot in class in various ways. But understanding that like charges attract each other and opposite charge, or sorry, I said it backwards. Opposite charges attract each other and like charges repel is a critical thing to understand. Okay, another property that we can talk about, let me see if I can erase this and get a little bit of space here, is the mass of these subatomic particles. So I'll tell you that protons and neutrons, the particles that are in the nucleus, these are heavy. Now, this is relative. They're not heavy. It takes like billions and billions of them to even equal a gram on a scale. And billions is small, actually. It's way more than that. But they're small. They don't weigh very much. They don't have much mass. But compared to electrons, they are the massive subatomic particles. So we could also say that each one of those has a mass of 1 AMU. And AMU stands for atomic mass units. So you know how like we measure, if I was going to put some grapes in the grocery store on a scale, I would measure those in like ounces or maybe pounds if I had apples, something bigger. We measured those, and that's a good measurement, ounces and pounds or grams or kilograms for bigger stuff. But protons and neutrons and electrons are so small, we use a completely different unit called atomic mass units. And so you'll never measure anything in atomic mass units because we actually can't really, but we can compare atomic mass units to things like grams. Okay, so make sure you've written down for the masses of the three particles, protons and neutrons, the things in the nucleus, are heavy, right? Electrons have an insignificant mass. Hopefully I spelled that right. C-A-N-T. Insignificant mass, okay? Meaning they do have a mass, but it's not significant enough for us to actually measure and include when we talk about the mass of an atom. One analogy I'll make is if we were going to weigh an elephant, okay, and I put an elephant on a big scale that's like for weighing trucks or large animals at a zoo or something like that, and I weigh that elephant, and then a bunch of flies come and land on the elephant, right? The mass of that elephant is really not going to change significantly when all those flies land on it. In that scenario, your protons and your neutrons or your nucleus is the elephant, right? That's really where all the mass is. The electrons are those flies. And that's a good analogy for electrons because in atoms, electrons can kind of come and go as they please based on different reasons we'll talk about later. But then protons and neutrons usually stay in the nucleus. So what does that mean now? That means that the real mass of any atom is in the nucleus. And so those are a few really important concepts, understanding those three subatomic particles, protons, neutrons, electrons, their charge, and then their mass. All right. Okay. The next thing that we'll look at is, like I said, this is all theoretical. We can't see any of this stuff. So how can I sit here and tell you that all of this is true? That we know that this is, 99.9% certain what I'm telling you is true right now. How do we know that? And the answer is through different experiments. And so I'm going to show you a couple of experiments that highlight how we've gained a little bit of knowledge of the atom. And there's so many, but I'm going to just show two to you.
The first experiment that we'll talk about that was helpful in determining the structure of the atom is often referred to as a Rutherford's gold foil experiment. This is a very popular example of where the experimenter was able to determine something about the atom, even though it's really small. So here's a gist of how his experiment went. Rutherford thought that if the model of the atom, or what scientists thought the atom was like, was called the plum pudding model, and that was the atom was spherical in shape, and that all of the particles that made up the atom just kind of floated around all over the place, and they were in random areas. And so, what he thought because of this, his hypothesis, based on his current information, was that if he shot a beam of alpha particles, which are positively charged particles, if he shot those at a very, very thin sheet of gold foil, and we're talking like thinner than tissue paper here, that all of those electrons, I'm sorry, all of those alpha particles would go straight through the gold foil because of the current model that he thought existed of the atom. So he went ahead and set up this experiment. And basically, what we're seeing is the gold foil was hung here in the middle of the experimental setup, and then there was this ring all around it with the fluorescent screen. And so if any of the alpha particles hit the fluorescent screen, it would glow a little bit. What he saw when he shot the beam of alpha particles, or turned this on, which you wouldn't really be able to see, is that a lot of the particles did go through and hit the fluorescent screen directly behind the gold foil back here. But actually, some of them bounced back and were deflected completely back to the screen. And that was not expected. And so from this, he actually learned a couple of things. One, figured out that most of the atom was made of space, because a lot of the alpha particles just went straight through that gold foil. But he also realized that there was a small dense area in each atom that was positively charged. And how did he know it was positively charged? Because it's deflecting those positive particles. And like we said earlier, like charges repel each other. So when those alpha particles did encounter a nucleus, they were deflected, as you can see in the picture down here. So his experiment was super important in the development of the structure of the atom. He was basically the first person to say that atoms are mostly space and that there is a dense nucleus and that's positively charged. The next experiment we'll talk about is J.J. Thomson's cathode ray tube. At J.J. Thomson's time, a lot of these scientists that we're talking about, they all kind of were in labs together in different areas of the world and worked together on a lot of these projects. But J.J. Thomson knew that there was these things called electrons, and he had the feeling that they were a part of the atom. And he wanted to create an experiment that would determine the charge of the atom. He wanted to know, are they positively charged, negatively charged, or do they not have a charge at all? So he set up a rather simple experiment. He created a cathode ray tube, which is a very common instrument used in labs and electronics. And he put a magnet across that cathode ray where these electrons would be passing. So this is a stream of electrons. And then he also put a charged positive plate and a charged negative plate. And he hypothesized that if electrons were negative, right, that they would curve towards the positive plate up here. And that's in fact what happened. Now, this little beam that we're looking at here, that he wouldn't be able to see that. So what he was really looking at here is another screen where when the electrons hit this screen over here, we would see the screen light up. It would give little blips, little phosphorescent light. And so, he also said, well, if the electrons don't have any charge, then they'll just pass straight through and hit the screen in the middle. And if they're positively charged, they'll curve towards the negative plate here and hit down here. And you can see from the experiment, the picture here, he was able to prove from this experiment that electrons have a negative charge. And so these are just two of many hundreds and hundreds of experiments that have happened to give us some idea of what the structure of the atom looks like. Okay, so now that we have some idea of where the atomic theory came from, just a little bit, there's a lot more to it. Let's talk some about how we represent atoms and what does it mean if an atom has a certain number of protons or neutrons or electrons. All of those things are really important. And those are some key topics we need to understand. So let's get into this a little bit. Here we have the structure of a lithium atom. And we want to be able to represent that lithium atom in a way that we can write on paper. And so we have a couple of ways of doing that. First, on our periodic table, which you should have in front of you. If you don't have that out, please have that in front of you right now, because we're going to refer to it quite a bit as we practice here. And so on the periodic table, you'll notice that there's a symbol for each of the elements, right? Li is the accepted symbol for lithium. Underneath that, you'll see the name of the element usually. Above that symbol, on most periodic tables, all standard ones, there's going to be a whole number, and that's the atomic number. And then underneath the name or symbol on most periodic tables, you're going to see the atomic mass. And so we're going to talk about the difference between atomic mass and mass number. So this box on the periodic table is one way to kind of represent or give information about a particular element. This is another way down here where we write the Li with the 7 above it on the upper left corner and the atomic number on the lower left corner. This is called a nuclide symbol. Nuclide here, see this nuclide? That just stands for nucleus. And so basically the nuclide symbol is telling us what's the composition of that nucleus. So what do these numbers mean? Let's start with atomic number. The atomic number can be written here. We find that on the periodic table, or on the nuclide symbol. It's here, the 3. And the atomic number for lithium is 3. And what does that number represent? That represents the number of protons. So if we look at our actual physical model here, or the picture of the atom, how many protons are in the nuclide or the nucleus? One, two, three. And so that number is represented here with a 3. And if we wrote the nuclide symbol, we could put that number down here as a 3. Now, what is that? Like, what does that tell us? What happens if, we change the number of protons? And I'll tell you, you should write this down. Okay, this is a key important thing, and highlight this. The number of protons is the identity for every element. It's its name badge. If I ever want to know what element am I working with, the only number that matters is the number of protons. The electrons and neutrons matter for other things. But if I want to know the identity of the element, I need to know the number of protons. Okay? So let's take that for a second and practice. Come to your periodic table. Let me bring mine up here. And um, let's do a couple of examples together. So here's what I want you to do. I'm going to tell you I have an element in mind here, and that element has 12 protons, 12 protons in the nucleus. So I want you to look at your periodic table, find the atomic number 12, and tell me, what element am I thinking of? And I'm thinking of magnesium, right? That's really easy. We're just looking at the top number. On your periodic table, you have a key even up here to help you remember the atomic number is the whole number above the symbol. So if I told you I have an element that has 12 protons, you would know without a doubt that that is magnesium, an atom of magnesium. And it can't be anything else, because every element that has 12 protons, every atom that has 12 protons in the nucleus is magnesium. Okay, so let's practice a couple more without my help. I want you to go ahead and find the element that has 35 protons in the nucleus. Take a second and look. 35 protons. And if you said bromine, you're right. Bromine, these elements here, bromine, chlorine, iodine, these are all used as cleaning agents because they're really good at killing bacteria. And bromine, if you've ever been to Disney World, the water at Disney has a particular smell to it on the water rides because they use bromine as a disinfectant instead of chlorine, like pools and stuff. So that's the element bromine. Let's do two more. Find the element that has, let's see here. This is a good one. 74 protons. Find the element with 74 protons. If you said tungsten, you are right. It's one of the most dense metals. In the old light bulbs that I used to have when I was a kid, they used tungsten filaments because you could get them really hot and they had a very, very high melting point and they gave off a lot of light, but they also gave off a lot of heat, so they're very inefficient. And so now in the last 20 years, we've switched over to complex fluorescent. Those are the little curly Q ones. And then most recently, fortunately, we've moved to the LEDs, which are super efficient. Okay. And also, I just want to mention, you'll notice that sometimes the symbol for an element doesn't match the name. Like, how? Okay, tungsten, and we're using W. Where's that coming from, right? Well, that's because a lot of the elements on the periodic table were discovered a long time ago. Way, way before America like even existed and things like that. And those elements were named for like Latin or places they were found, and those names have stuck. And so you'll see things like where's lead at? PB over here. I lost you. Here we go. Atomic number 82. So it has 82 protons in the nucleus, right? PB stands for plumbum, because plumbers used to or sorry, the lead lead was named after the Latin word for it, plumbum, and that's where we get our term plumber from. This because a lot of pipes and stuff used to be made out of lead, and so there's some connections there. And then of course some of them match. If you come up to sulfur and it's just S, or chlorine or bromine, Br, that they make a little bit more sense. So sometimes that throws us off when we're trying to identify different elements. Okay, I said two more, so let's do one more. Find the element that only has 2 protons in its nucleus. Right, atomic number 2 is helium, and you have probably sucked that out of a balloon at one point and listened to your squeaky voice, which is always fun to do. Just don't do it too much because you don't want to pass out and hit your head or something. All right, so we get the idea here. Now let's go the other way. And what if I told you, all right, I want you to tell me or draw a picture of an element that I give you the name and you have to tell me how many protons it has. So this is something that we need to be able to do as well. So I want you to find, I'm gonna point to it here just to help us along. Iodine. So if I asked you how many protons does iodine have in its nucleus, you would say 53, right? Good. If I came over here to francium, which is actually the largest element in terms of the atomic radius, it's not the heaviest; it's the largest. Francium is, you can imagine what it's named after. You can tell me how many protons. Can you tell me how many protons it has in a nucleus? 87, right? Okay, I think we get the idea. This is not hard, but we want to practice that a little bit to get it down. So big point on that one that you should have written down: the atomic number is the number of protons. The number of protons is the identity of the element. If we changed somehow, this isn't normal, but if we did change the number of protons in a nucleus somehow, like through a nuclear reaction, the element is going to be different. Protons change, element changes. Okay, it's its name badge. All right. Let's go back to our slideshow here and keep talking about some of these other numbers. And so I want to next talk about this number here on the nuclide symbol. And so what is mass number? And mass, remember we talked earlier that the heavy subatomic particles are the protons and the neutrons, and those are the ones in the nucleus. The nucleus makes up the mass of the atom. The electron mass is insignificant. So when we want to count the mass of an atom, we want to count how many protons and neutrons are there. Now, the mass number is always a whole number because we can't have a half of a neutron or a half of a proton. It's always, you have, one or none. So those are whole numbers always for the mass number. And we'll talk about why. We'll talk about atomic mass here in just a minute, because that is a different number. You'll notice here lithium has a mass number of 7 for this lithium isotope, and yet the atomic mass here is 6.9. So how do we get that? We'll talk about that in just a second. So let's go ahead and, if you're on your paper here, let's flip it over because we should be done with that. Lots of good information so far. Lots of new vocabulary potentially for you. So what's the atomic mass of lithium? Now that number is going to be on the every periodic table. It's an experimentally determined number, and it's very consistent from one periodic table to the next. So this number right here, the mass, atomic mass, not mass number, atomic mass of lithium from the periodic table is 6.941. Okay, you can see that on your periodic table. It might be rounded to a less number of decimal places. So where does that number come from? That's what I want to talk about next. This question confuses students a lot of times because they'll think, oh, if I'm asked the mass number, I just look at the atomic mass. And that's not true. The mass number is used to tell us what specific isotope of an element we're working with, and the atomic mass is an average of those. I want you to skip the question that says, what is atomic mass or what does this number represent? We're going to skip that real quick and go on and talk about isotopes for just a minute. Okay, so again, we want to talk about our next concept of isotopes, and that's going to help us understand the difference between atomic mass from the periodic table and mass number. So I want you to look here at the 3 different isotopes of lithium. And let's talk about what's different about each of these lithium atoms. Well, first of all, what's the same? What we know is the same is the atomic number. Why is that? That's the number of protons. So that's also the identity. So in order for all 3 of these different atoms, these different isotopes to be lithium, they have to have 3 protons. If they had a different number of protons, they would be a different element. We've already covered that. What's different though? Up here we'll see the mass number. Remember, mass number is always a whole number because it's the addition of the protons and the neutrons and the nucleus. So this isotope of lithium has 6 for its mass number, a mass number of 6. So we would call it lithium 6. This lithium atom or isotope, this isotope of lithium has a mass number of 7, so we would call it lithium 7. And this one has a mass number of 8, so we would call it lithium 8. So what's different about each one of these? They're the same element, but they have different mass numbers. So anytime We have two elements that are the same element. They have the same number of protons, but they have different numbers of neutrons in the nucleus. Then those are considered isotopes. I want you to think about isotopes as like different versions of the same type of atom or element. You can see here, I've got like three different, if you will, like models of lithium. Think about like different cars. You've got like different models of, let's see, like a Subaru Outback or whatever. There's like the low end model, the medium, and the high end model, and there's some differences about each one of those. Those are still all Subaru Outbacks, but there's something different about each one. And for atoms, we have the same thing. These are all lithium atoms, but they are different because they have different number of neutrons in the nucleus. You might think like, how why is it that this is true? Like, why does are there different masses of lithium? Why can we find different isotopes of the same element on Earth? And to show you that and illustrate that, let me bring up a build an atom FET here. You can get to this if you want to play around with it while we're going through these notes. This will be helpful, and we'll actually play with some together here in a bit to practice. So to get to this, you can just Google PHET, which is FET, and start typing build an atom. This is also linked, I believe, on Google Classroom if you just want to go there and pull it up. And we'll just start with the atom page. And what this allows us to do is build an atom and see what changes about it. And so for now, I'm only going to open the mass number here, which is going to show us the total number of protons and neutrons that are in the nucleus as we build the atom, and then the element here. So let's go ahead and build lithium. I'm going to start putting protons in the nucleus. For now, I'm not going to worry about the charge, and so I'm going to ignore electrons for now. So I'm going to actually take off neutral ion here, or ion. All right, so again, let's just review. I've got one proton in the nucleus, so we're at hydrogen here, right? Let's put another proton in the nucleus. I'm trying to get to lithium. And let's put another proton in the nucleus to make it lithium. All right, so 3 protons means we have lithium. Now, you'll notice that this atom of lithium is unstable. Let's think about why that might be. What charge do protons have? Positive. And what have we just done? We've put a bunch of positively charged things all in the same space together. And what did we say at the beginning of the lesson? That's like a foundational law of science and nature, that things that have like charges don't really want to be near each other. And so, really, the tendency is that protons want to be away from each other, but we're trying to cram them all in the same space. Well, now comes the neutrons. When atoms form through different processes, which we'll learn about later, usually neutrons are in the nucleus as well. And neutrons act as kind of like a buffer, or a proton glue, if you will, just for lack of another term. There's a lot of nuclear science here and different forces, like the strong force and the weak force. And we're not going to get into all of that. Maybe you will in higher level classes. So neutrons are going to allow the protons to be more stable, if you will. So as I add neutrons, what you're going to see happen is when I get to a certain amount, now I have enough neutrons in the nucleus that the protons don't all have to be close to each other. This is sort of like if you had two siblings that were fighting each other, and you get in between them so that they can't beat each other up or something like that. Maybe think of it like that. These neutrons are helping to stabilize the situation. Now, what's the right ratio? Like, how many do we need? You saw if I only had 2 there, that wasn't enough. So, what that means is, if when this particular lithium atom that I'm showing you, if it formed like this, it wouldn't exist. It would kind of, if you like, fall apart, if you will. The nucleus wouldn't be stable, and it would go through a radioactive change, which we'll talk about in another unit as well. So now if I add another neutron, now we have the right amount, like a 1-to-1 ratio, but it doesn't always have to be 1-to-1. You'll see if I add, and by the way, look at the mass number here. Right now, the mass number is 6 because I have 3 protons and 3 neutrons. Now I can add another neutron, and it's still a stable atom. So this is another atom that if it formed, it would be good. It would stick around, and we would find it in nature. And so you can see here its mass number is 7. What that's telling us is I can find in nature lithium atoms that are lithium 6, and I can also find heavier versions of lithium that are lithium 7. Those two are naturally occurring because they have a stable nucleus. What happens if I add another neutron? Now this becomes unstable. And if this formed in nature through a nuclear process, it would decay or go through some nuclear change and change until it was stable. So you can see that, excuse me, as we go through and look at these different elements, there can be different versions or different isotopes that have different numbers of neutrons in the nucleus. Now, every one thing that students get confused about is they think that the nucleus of an atom can just change, like we can just add some protons or take away some neutrons, and that doesn't normally happen on like a regular basis. It can happen, and that's called radioactive decay, and so we can actually see a unstable nucleus of usually heavier atoms can decay and become stable over time. And we'll talk about that again whenever we talk about radioactive dating, radiometric dating in our geosphere unit. So um, uh, uh, atoms form, and when they form quickly. If they have a stable nucleus, they'll stick around and we'll find them in nature and naturally. If they don't stick around, we won't find them if they're not stable. Okay, so back on the note sheet, let's just write a few things down if you didn't already. The first question was, what is an isotope? And I think the easiest way to define that is it's uh, atoms that are the same element but have different masses. And if you need to pause to write this down, go ahead. Atoms that are the same element but have different masses. And just on that note sheet, it said back here what was the same about each. We already went over that. Each of these isotopes of lithium have 3 protons. That's what the same. But the difference is kind of two differences, right? They have different numbers of neutrons in the nucleus, which also means they have different mass numbers. And when we want to specify, if it's important to specify which isotope of an element we're working with, we would just call it the element name. And then after we call it its name, we would say what the mass number is. So, like I said before, if I'm doing research with lithium and I want to specify that I'm working with lithium with a mass number of 6, I would just call that lithium 6. It wouldn't make sense to call it lithium 3, right? Because all lithium has 3 protons, but not all lithium has a mass number of 6. This also reminds us too, remember that all mass numbers are whole numbers because it's protons and neutrons in a nucleus. Okay. Now that takes us back, well, before we move on, I want to come to an interesting periodic table here. This is a periodic table of the known isotopes of all the elements on Earth. So if we look at this, let's go to lithium. Okay. What this is telling us is that lithium, there are 10 known isotopes, but only 2 of those isotopes are stable. And so I just showed you that in this this example, right? We saw lithium 6 and lithium 7 were stable. Those are the only 2 stable isotopes. And you can see if you look at this periodic table, most elements that we find in nature, many of them, have more than one stable isotope. Some of them only have one. You can see here, like beryllium, we only really find one stable isotope. Sodium, we only find one stable isotope. But some of them have more. So, like neon here, neon has 3. We find 3 stable isotopes. Sulfur has 4. And how do we know all this? This has just been done by researchers. They've tested and samples, that have a lot of atoms and figured out through with special equipment, very expensive equipment that you usually find at universities and high tech labs. They figure all this stuff out and disseminate that information to us. Um, and so now this takes us now back to our question that was previous to this slide on isotopes. Like, what is mass number or atomic mass? Mass number is whenever we have we're talking about a specific isotope, we can say the mass number. But on our periodic table, if we look at that, right, all of these, oops, I'm gonna have to reload, sorry. All of these masses are not whole numbers. And what they really are is a weighted average of the different isotopes that exist. So I'll focus on lithium still here, okay? Remember, we said there were two stable isotopes of lithium, lithium 6 and lithium 7. Well, what scientists have done is said, well, if I have a really big sample of lithium, I'm going to have some lithium 6 in that sample that has lots of atoms of lithium in it, and I'm going to have some of lithium 7. And there's a certain percentage of these isotopes found in nature. So, what the scientists have done is done a weighted mass of the different isotopes so that if a scientist ever takes a sample of lithium, they know this is going to be a good number to use, the 6.9 for the um, atomic mass, as an average of the lithium atoms that exist on Earth. And, for now, that won't be super important for any of our calculations and whatnot, but it is important to understand that. And as you move into higher level classes, um, understanding that we'll use that atomic mass for doing calculations and whatnot is going to be important. So now this brings up a question. What if I asked you, I came over here to carbon and said, well, okay, how many protons does carbon have? 6, right? Well, how many neutrons does carbon have? Well, you can't really answer that question because you don't know which isotope of carbon I'm talking about. The best we could do is come down to the atomic mass here and round it to the nearest whole number and say, okay, well, the if the atomic mass of carbon atoms, all the different isotopes, is an average of 12.011, then I'll just round that to 12. And then we can say, well, if we're talking about a carbon with a mass number of 12, I could do 6 or 12 minus 6, right? And that would give me 6 protons in the nucleus, or 6 neutrons in the nucleus. So the point is, it would need to tell you either the mass number or how many neutrons there were. You can't really determine that from looking at the periodic table. Okay, so let's go ahead and move on to, well, let's come back to build an atom here and play around a little bit more. We're not going to get to ions yet, so let's practice. I'm going to give you a couple of tasks to do. So the next thing I want you to do, if you haven't brought this up, go ahead and bring it up, and I'll pause in between each of these. I want you to build an atom of carbon that has a mass number of 6. Go ahead and turn off down here. Go ahead and turn off where it says neutral or ion, or just ignore that if you want. All right. And go ahead and expand the mass number so you can see what that is. So pause and take the 10 or 20 seconds to build a carbon atom that, I'm sorry, I said 6, that has a mass number of 12. A carbon atom that has a mass number of 12. Okay, pause and go. Okay, so we would know to make it carbon, we have to have 6 protons. And now to make it have a mass number of 12, so it would be carbon 12, I also need to add 6 neutrons, right? And this is a nice visual for you because you're seeing up here as you add things what you're changing. And down here, you're seeing the mass number, and here you're seeing the element. So this is a good way to check. Okay, next one I want you to do, I want you to change this and make it, and let's see, let's go ahead and make an oxygen atom, an isotope of oxygen. And let's do oxygen, let's say oxygen 16. Go ahead and make oxygen 16. Pause and go. To do that, right, we need to add 2 more oxygen, or 2 more protons to the nucleus. And if we kept that carbon the same, we'd still need to add 2 more neutrons. And I don't have the stable unstable, but you'd see that is oxygen 16 is a stable isotope of oxygen. So is oxygen 17 and oxygen 18. So those are 3 stable isotopes of oxygen. When we do radiometric dating or carbon dating, we use one of the different forms of carbon. I guess it's not related to oxygen. Let's do one more. Let's go ahead and reset it. All right, go ahead and open this up, turn this off, and go ahead and make a an isotope of, let's see, let's go ahead and do helium. And let's make helium 5, helium 5. Pause and go. Okay, to do that, we would need 2 protons because that's how many protons helium has. And then we'd need to add 3 neutrons to get to a mass number of 5. So that would be helium with a mass number of 5, which we call helium 5. Okay, good practice there. Now, I want to pause really quick as well and just remind you how we would write this. How would we write helium 5 if we were going to write the nuclide symbol for that? So we would come here and we would first find the symbol. We know it's helium, so we would just write that. And so what's going to go here and what's going to go here? Down here, as we talked before, is the atomic number, which is also the number of protons. And for helium, it's always 2. Now, sometimes you will not see this written here, the 2, because it's kind of redundant, right? We know if it's helium, it always has 2 protons. So we could always look at the periodic table and just say, oh yeah, helium has 2. So sometimes you'll see the nuclide symbol with that written and sometimes you won't. Now, the mass number is very important. And we said that was helium 5. That's what's going to go here. If you ever have a nuclide symbol like this that's set up like this, all right, this is a nice little way to find out neutrons. We know this is protons plus neutrons right here. And we know this is protons. So if we set up a little subtraction problem and do 5 minus 2, that gives us 3 neutrons. So that's an easy way to find how many neutrons there are if you know the mass number. All right, so that's just a little practice writing nuclide symbols, which you'll need to know how to do, and also how to interpret. Like if I'm giving you one, what does that tell us about that element? It's protons, neutrons, electrons. Okay, we haven't talked about electrons yet. That's going to be our last topic. So isotopes, now ions. Um, let's go to our last slide in our slideshow. And what I have here is, again, 2 different atoms of lithium. We're not going to worry about the mass number on this one. The mass number is the same for both. Now we're going to start talking about electrons. Electrons come and go for atoms all the time. Atoms can lose electrons, they can gain electrons, they can share electrons. We'll talk more about why they do that when we discuss bonding. So what you need to understand is the amount of protons in the nucleus and the amount of electrons determine the charge of the atom overall. And protons are obviously positive, electrons are negative. And if we have a 1-to-1 ratio, meaning we have the same number of protons, like in this atom, we have 3 protons that are positive and 3 electrons that are negative, those kind of cancel each other out, right? Because we have the same amount of each. So we would call that a neutral atom, and it doesn't have a charge for that atom. So if we come down here though, in this example, this is a lithium ion. And what's happened is this lithium atom here has somehow lost an electron. We'll talk about why that might be later. But you can see it has 3 protons still, because protons are pretty stable. They stay in the nucleus, right? They don't come and go like electrons do. And now I only have 2 electrons. So if we think about that, I have 3 positive charges and 2 negative charges. So what does that give me overall? It gives me a +1 charge. I have 1 more positive proton than I have electrons. So I'm just comparing those two, right? If I was going to show you that visually, right, I'm going to come back to the build an atom, and this was lithium. So we'll rebuild lithium. I'm going to put the charge on here. And we started out with a neutral lithium atom because it's not charged. And you can see that here. Look at my charges: 3 positive, 3 negative, 3 protons, 3 electrons. So it's neutral. Now, what happened, we said in that second example here, is that this lost an electron somehow. So again, this visual shows you these two cancel each other out, but since I have 1 more positive charge, this has a net or overall charge of +1. And when we write that, the symbol for it, we show that it has a charge by putting the charge in the upper right corner of that nuclide symbol or the element symbol, like a plus right here. So let's look at the notes really quick. This just to make sure you have some good information written down here. What's the difference between these 2 atoms of lithium? One is neutral and one is an ion. And why does lithium have a positive charge in this example? Because it has more protons than electrons. If you need to pause to write that, you can. How do we determine the charge of an ion? So if we have an atom and we want to know the charge, how do we do that? There's a couple of ways. Um, First, we can just think about that logically. Like I'm saying here, okay, if I have an element and it has, let's say, 5 protons, 5 positive, and it has, let's see here, and it has 4 electrons, we know it has one more positive charge. So we're kind of just doing a little bit of math in our head here. And so we would have an overall charge of +1. And what if I had an element that had more electrons than protons? So this would be neutral. Let's add one more. Okay. Now we have an overall charge of -1 because there's one more negative charge overall, one more negative electron than there is positive protons. So we can think about it logically. We can also just do this mathematically. So mathematically, if I said I have, let's see here, let's go to the whiteboard. If I said I have 5 protons, right, which is a positive, and what did I say? 6 electrons. 5 minus 6 is -1. So basically, mathematically, we can add those two numbers together, putting the positive on the number of protons and the negative. And when we put those numbers together, 5 and -6 gives us -1. So we're really just adding those two numbers together. What if I had 5 protons and 5 electrons, right? That would give us 0. So that has a net charge of 0. What if I had 5 protons, same element, and 4 electrons, right? Now I do 5 minus 4, that gives me a +1 charge. So we can think about it logically. You could draw it out if you want until you're more comfortable, or mathematically, we can just add the positive and the negative together and see what we get. Now, what if it's not just one? What if it's multiple? So let's take a look at that. Same principle. If I go to, let's see, I can't do magnesium. We'll go to oxygen here. I'm going to make an oxygen atom. So carbon, nitrogen, I'm adding protons, so I get to oxygen. Now let's throw some more electrons in here to make it neutral. Okay. But what I'll tell you, this is neutral because it has the same number of protons and electrons. Oxygen really likes to take 2 electrons from other elements. And so if I add 2 here, look what happens, right? Now I have not just 1, but -2 is the charge. So how would we write that? Come back here, we'd write the element symbol, oxygen, and we would put 2 minus up in this upper corner. So if you have an element like lithium that only has a +1 charge, we don't need to write the 1. We can just do plus. Or an element like chlorine that likes to form a -1 charge, we can just put minus. But if there's ever more than just 1, we have to include the number here of the charge. Okay. All right. So let's go ahead and go back here, and I'm going to give you a couple of tasks like I did before. We'll leave out mass number for the first two, and then we'll practice with mass number as well. So go ahead and reset, open your net charge, leave neutral and ion, go ahead and leave that on now. And let's go ahead and make let's see here, let's make a fluorine atom that has a -1 charge, fluorine with a -1 charge. And don't worry about neutrons. Let's just go ahead and do the protons. Okay, go pause and create your fluorine atom that has a -1 charge. Okay, we're going to use up all of our, almost all of our protons, right? There's fluorine. And if I start putting electrons in here, you should get to neutral once you have 7. All right, and oh, I'm not there yet. Neutral. Okay. And now to add one more electron is going to give us that -1 charge. How would we write that? We would come here and say this is fluorine F negative. That's all we have to do for that. Okay. All right. Let's do another one. Go ahead and change what you have here to make a nitrogen atom with a -3 charge. Nitrogen atom with a -3 charge. Pause and go. Okay, all we had to do was take away some protons in the nucleus. Nitrogen, when it has a -3 charge, it's going to have 3 more electrons than those 7 protons that are in the nucleus. Okay, so again, how would we write that? Come back here, write the symbol, and we do 3 minus. Okay. Notice I'm not putting the mass number because we're really not focusing on that, but we could do that. So now let's go ahead and do that. I want you to make, let's go ahead and leave it nitrogen with a 3 minus charge, and let's make it nitrogen 15. Nitrogen 15, that's a -3 ion. Pause and go. Okay, so all I'm doing is adding the neutrons to the nucleus until I get to the correct mass number that I asked you for, which is 15. So how would we write that if we wanted to write the full nuclide symbol? Now we would put the 15 here. And if we wanted to, we could put the 7. We don't have to. But this would be like the full nuclide symbol for that atom we just built, right? It's a negative ion with a mass number of 15, atomic number 7. All right. Okay, good. Let's do one more. Go ahead and create um, an isotope of boron with let's make a boron 10 that is a +2 ion, has a charge of +2. Go. Okay, so we had to take a couple of neutrons out of the nucleus, and now I'm removing some of the electrons, and I wanted to have a +2 charge, right? And so that we would have 3 electrons in order to create a +2 charge. That would give us 5 protons and 3 electrons for a +2 charge. And then if we wanted to write that, do this one more time because you guys are probably getting it by now. Okay, oops, did I do the right mass number? I think I said boron 10. My apologies. So I need to take a couple of neutrons out of here. Okay, boron 10 with a +2 charge. So that would look like this. Boron, mass number 10, +2 charge. Boron has 5 protons in the nucleus. Okay. All right, good. Um, Hopefully that gives you like some idea of like what these different numbers mean and all of that. One thing I will point out that I didn't mention yet is you'll notice these dotted lines. That's because electrons have specific places around the nucleus where they are allowed to orbit based on the laws of physics. And that gets kind of complicated. We're not going to talk much about it, but I will tell you the first energy level, remember these are called energy levels. The first energy level can hold 2 electrons, the next one can hold 8, and then it goes to 18 and so on. It gets bigger and bigger because there's more space for those negative electrons to spread out. And it's a little more complicated than that, but I'm simplifying it for our purposes here. So the next thing to do is to practice this a little bit. And so I think a great place to practice is to come down here in the place where we're at. If you want a little more practice seeing the symbols, you can play with this tab. And if you want to play some games, there's 4 different games here and they get progressively harder. So I'm going to ask you to take about 10 minutes to come here, and click on each one and determine based on what we've talked about the right answer to each of these questions. So to start off, really easy. This is an element that just has 1 proton. We know that that would be hydrogen. So we click on hydrogen, and now it's asking, is it neutral or an ion? So we got to think, does it have the same amount of electrons and protons? It doesn't have any electrons here. And so we have 1 positive charge, no negative charges. This must be an ion, right? It's good. So go ahead and take about 10 minutes and get as many of these stars as you can. Oops, let's see here. As many of these to 5 stars as you can in about 10 minutes. And then you can move on to the practice that I've provided for you.